under the surface of oceans and lakes. Inside the eggs of birds. And in the uterus of mammals, we arrive to life in water. Without this exceptional molecule, none of us would even exist. It has absolutely unique and life-supporting properties that have baffled scientists for decades.
All liquids on this planet, all of them behave in a similar manner. And then water completely misbehaves. It's like a child that you cannot control. The normal liquid would be like alcohol, oil, ether, any type of liquid, which typically behave in the same way, and water sticks out. Usually, if we have a solid, it's more dense than the liquid.
If you take a glass of alcohol and then freeze the alcohol with liquid nitrogen, the frozen pieces are heavier and more dense than the liquid, and they sink.
But take a look at the glass of ice water, and you will see that the ice floats on the water. That's actually quite peculiar that the solid is actually less dense than the liquid. It's mysterious. You will see that the temperature at the bottom of the glass is 4 degrees Celsius. So water becomes heaviest at 4 degrees.
If ice had been heavier than liquid water, the cold ocean floors of the planet would be covered with endless ice and would never have enabled life on Earth. A crystal clear liquid composed of a chemical compound hosting nothing else than that.
Water has a very high surface tension, much higher than nearly all other liquids.
Surface tension is only a few layers of strongly bonded water molecules that can carry enormous weight in relative terms, such as a razor blade of steel. But just a small drop of soap replaces the top layer and the tension disappears.
Water is a kind of a mystical thing for me. It has a kind of gravitation, like it attracts the interest. It's an open puzzle, so to say, that is calling for an answer.
If you follow the logic, water should boil at very low temperature, and then life around 20 Celsius should not exist because water would be a vapor. But because of the hydrogen bonds between the water molecule, the existence of the liquid state is typically between 0 and 100 Celsius, which is exactly where life can occur.
There are 20 anomalies or even more anomalies which deviate strongly from all the other liquids we know. And they are not deviating by 1% or 2%, so it's dramatically different.
And we're still trying to understand why that is. Why is this anomalies appearing? What is the origin of these anomalies?
In Boston, back in the beginning of the 1990s, a group of physicists, Francesco Scortino, Gene Stanley, and Peter Poole, started to come close to water's secrets by using computer simulations.
I've been studying water for 30 years more nowadays. And at that time I was doing numerical simulation.
And it's during the computer simulations that the scientists suddenly make a key discovery. Inside the calculated network of water molecules, they detect signs that water can exist as two different liquids, with structures that would link water molecules to each other in very different ways.
And today, after 30 years of studies, we have realized that these anomalies arise from the competition of two different local structures. It's completely new, a completely crazy idea. Right? And it was crazy 30 years ago. No one has ever tried to propose anything similar to that.
The approach could be done either this way, and this forms a very open structure, or this way, and this forms a more compact structure. The way in which these water molecules approach each other while they move and dance in the liquid, we know that this kind of fluctuation between a low density and a high density liquid do exist already at ambient temperature.
The dance of fluctuating local structures shows how density maximum in water appears. At 100 degrees centigrade, we have only high-density red molecules that move rapidly. As the temperature lowers, the molecules move more slowly, decreasing the volume of the water in the glass and increasing its density. At 50 degrees, we start to see the appearance of low-density blue molecules, and when the temperature decreases further, the low-density regions grow and the water level in the glass stops sinking, since the blue molecules take up more space. When the water has reached its density maximum at 4 degrees, the liquid is balanced between the tight red molecular structures and the blue area ones. Between 4 degrees and 0, the blue airy version of water takes over and the volume in the glass rises. But there is one problem. The two-liquid water is just a hypothesis presented through computer simulations. And there are several other competing theories to explain these water anomalies. In the end, it's all about experimental testing with the actual substance, water.
The hypothesis of two liquids has, of course, eluded the scientific community for decades. And I started thinking about this, how such an experiment could be done. So when water is hot, it behaves like all the other liquids. It is when it gets cold, it becomes more and more strange. Because what could be happening there could be the origin for water's strange properties also in our conditions. It's just amplified.
How to study water extremely fast before it freezes. To use a super exclusive tool based on X-rays and to try it on pure water.
And following all the ideas, what it could do, it became very apparent for me that we can open a complete new door in water science by using X-ray lasers.
The team freeze water under high pressure, but later at the X-ray laser experiment, they can warm up into the liquid phase and search for the two liquids.
If we compress the ice at very low temperatures, we talk about temperatures of minus 200 degrees centigrade, then this crystal structure collapses and suddenly forms something that we call amorphous ice.
By quickly heating them up in the X-ray laser, they hope to catch a glimpse of the two liquids right there in the fraction of a moment when the water molecules go from solid to moving. In a tiny ring with holes, they've prepared their ice samples, less than a millimeter thick. The sample ring is placed in the X-ray laser experimental chamber. With a powerful infrared laser pulse, they heat a tiny part of the glassy ice sample, and almost instantly, 10 nanoseconds after, they take a picture with the help of the brand new X-ray laser, exposing the result on a detector screen behind the sample. A flash much shorter than a trillionth of a second. The ring pattern on the detector screen shows the structure of the liquid. After the heating pulse, the liquid expands towards room pressure. Subsequent X-ray pulses will follow how the structure evolves. During the expansion, if there is only one curve present, it indicates only one liquid phase. If instead two rings are generated next to each other, it would be evidence of two liquid phases. And the first shot, after 10 nanoseconds, shows just that. One bright, narrow curve indicating one liquid phase of water. But now things are starting to happen. The next shot towards the sample is fired at 100 nanoseconds after the heating beam. And here, a second ring starts to appear. And with the third shot, after 3,000 nanoseconds, the second ring is even brighter. At last, their endeavors pay off. The experiment is a success. They have pictures of the two liquids of water. They struggle with analyses, evaluations, and rewriting, and eventually, it's sent. Now, they just have to wait. And finally, a very pleasant surprise arrives in the Stockholm lab.
Okay, so I just posted this on Twitter. Our article came out today on Science. You can see the date here, 20th of November 2020. Very exciting stuff.
So let's open the champagne. Cheers.
This paper is super important and very exciting because it's the first time that we have experimental evidence of this liquid and liquid transition in water.
We know of water as the liquid of life, but as science now has shown, maybe it has a more profound impact on the life process than previously understood. Maybe water works as a kind of computer network of nature, and maybe the two liquid structures of water could be the ones and the zeros.
So if water enables certain structures of molecules, then you could, of course, extend this and think of the water as some kind of matrix that transports information from one molecule to the other.
A low density pops up somewhere in the liquid, high density pops up somewhere in the liquid, and if we have a biomolecular protein, a DNA, a membrane in the cell, these fluctuations might no longer be random. And if these fluctuations are extended over a very long length scale, just like Sylvie have demonstrated, it could be possible that that actually is the mediator. Water is the mediator in this communication.
So when things happen in the left end of the cell, the right end of the cells knows about it, feels that something has happened at the other end of the cell within time sequences which are nanoseconds, picoseconds, are the most short, possibly short time sequences. And what role does water have in that?
And future experiments has to test this hypothesis. Could it be the question about the structure, dynamics, rearrangement in the liquid form of the water molecules, and its connection to the life processes is one of the major scientific questions of our time.